Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. We are moving towards extending our understanding of signed areas from splines to curves. And as a preliminary for that, I want to go over some important transformation properties of the signed area in the context of splines today. So let me just review that our basic orientation starts with the idea of a cross product of two vectors. AB cross CD is AD minus BC, that number. And then in terms of the cross product, we define the signed area of an oriented edge, A1, A2. There's an oriented edge. First point, second point, joined by a segment with an arrow halfway in between. And the signed area of that is, by definition, the cross product of OA1 by OA2, all divided by 2. Okay, so that's the definition of the signed area of an oriented edge. And then we extend that to signed areas of oriented splines. The signed area of the oriented spline A1, A2, A3 is the sum of the signed area of A1, A2 and the signed area of A2, A3. And we can also talk about the signed area of a cyclic oriented polygonal spline, A1, A2, A3 with a double arrow over it. What that means is that we're starting at A1, going to A2, then to A3, and then coming back to A1. So we could represent that with another line, this one here. There, now we see the cyclic-oriented polygonal spline A1, A2, A3. And in that case, the signed area is the sum of the signed area of A1, A2, and the signed area of A2, A3, and the signed area of A3, A1. The net effect is that these three triangles that you see here, there's some partial cancellation, and we just end up with what we ordinarily think of as the area of that little triangle there. Okay, so it all comes down ultimately to this idea of the cross product of two vectors. So we're going to be talking about two main theorems today, and the first one is the signed area translation theorem, which tells us exactly what happens to the signed area of an oriented spline when we translate it. So suppose that we have points A1 through to AN, forming a spline, and we're going to translate each of those points by a fixed vector v. So we'll let AI prime be AI plus v. And I remind you that in this course we are allowed to add vectors to points to get other points. Then the statement is that the signed area of the oriented spline A1 prime, A2 prime up to AN prime equals the signed area of the spline that we started with, A1, A2 up to AN, plus an additional term. And the additional term is the cross product of V with the vector A1, AN. That cross product divided by 2. So the vector joining the first point to the last point, that's that vector there, and V is the vector that we're translating everything by. So that's the adjustment that you have to make to the area of a oriented spline when you translate it. Now we're going to prove it in two stages. The first thing is just a sort of preparatory lemma, which is a special case when we just have 2 points. So suppose we have 2 points A and B, and we translate both of them by a vector v, giving us A prime and B prime. Then the lemma is that the signed area of A prime B prime is the signed area of AB plus V cross AB all over 2. Okay, proof. So what is the signed area of A prime B prime? Well, we have to take OA prime cross OB prime and divide it by 2. Well, what is OA prime? The vector from O to A prime. Well, that's the sum of the vector OA and the vector V. We go from O to A and then we add V, and that's how we get to A prime. So OA prime is OA plus V, and similarly OB prime is OB plus V. So we have to take that cross product and divide by 2. Okay, now the distributive law applies, and we get 4 different products. We get OA cross OB. We also get V cross OB, which is included here. And we also get OA cross V, which is the same as V cross minus OA because of the antisymmetric property of the cross product. So those two terms can be combined as V cross OB minus OA. Now there's a fourth term, which is V cross V, and that is always 0, so that doesn't figure. So we have those terms all divided by 2. Well, this first thing here, OA cross OB divided by 2, we recognize that's just the signed area of AB. And this other term here is V cross AB all over 2, because OB minus OA, vector from O to B, minus the vector from O to A, that's the same as the vector from A to B. That's the proof of the lemma, the special case of this theorem, when we just have 2 points in our spline. So let's illustrate the previous lemma with this picture here. Here we have oriented edge AB, and we're translating by V. So we go V in that direction to get A prime, we get V in this direction to get B prime. So we've gone from the oriented edge AB to the oriented edge A prime B prime. And what we're interested in is relating the signed area of the original spline AB with the signed area of the new spline A prime B prime. So the relationship between the green triangle and the red triangle. And what we've just determined is that the red triangle is the sum of the green triangle, the signed area of the green triangle, plus an additional compensating factor, which is V cross AB over 2. There's V, or also there's V, and there's AB. This is also AB. I'd like to give you an interpretation, a physical interpretation of this quantity over here on the diagram. So we could do that by drawing an auxiliary triangle. If we take this parallelogram here and we go from here up to there, then this triangle here, if you look at it, okay, it has one side is V, and this side here, A prime, B prime, is the same as the vector AB. This is the vector AB, so it's equal to the vector A prime, B prime, because this is a parallelogram. And so this quantity that we're adding here is exactly the signed area of this oriented triangle, A prime, B prime, because V cross A prime, B prime is another way of expressing what that signed area is, divided by 2. This cross this divided by 2. Okay, so now let's go to the theorem itself. So here's the proof of the theorem, where we have endpoints now. Okay, so we have endpoints, A1 prime, A2 prime, up to AN prime, obtained from points A1 through AN by translating all of them by a vector V. Okay, so what do we get? Well, first of all, by definition, the signed area of such a spline will be the sum of a lot of signed areas of just oriented edges. So it's the signed area of A1 prime, A2 prime, and then the next one will be signed area of A2 prime, A3 prime, and so on, all the way to the last term, signed area of AN minus 1 prime, AN prime. Now, each one of these we can apply the lemma to. So the signed area of A1 prime, A2 prime is the signed area of A1, A2 plus this additional factor, V cross A1, A2 all over 2. And there will be a similar expression for each one of these things all the way up to the last one, which is replaced with the signed area of AN minus 1 AN plus V cross the vector AN minus 1 AN all over 2. So altogether, when we look at the sum here, if we peel off the first entries of all these combinations, the S A1 A2 plus the S of A2 A3 all the way down to S of AN minus 1 AN, we just get the signed area of the original spline A1 A2 up to AN. And then what's left over are all these terms, and they all have a V in them, so we can pull that V out by distributivity. And it's V cross A1 A2 vector plus A2 A3 vector all the way up to AN minus 1 AN vector. So all of those terms, and then we have to divide by 2. And then this is a sum of vectors. The vector a1, a2, plus the vector a2, a3, all the way up to this vector here. They combine to just give the vector a1 to an. So altogether we get the original spline signed area plus v cross a1 an all over 2. And that's the statement of the theorem. So when we translate a spline, even though it may be very complicated, the way the signed area changes is actually reasonably amenable. It just changes by a certain amount, which is given by the cross product of the vector that we're translating by the difference vector between the initial and the final point of the spline, divided by 2. Now there's an important corollary to that, which is that if the spline is cyclic or closed, then its signed area is invariant under translation. So the proof? Well, in the language of the previous theorem, if the initial point, a1, equals the final point, an, well then this vector a1, an that we're taking the cross product here with is the 0 vector. And so this quantity will necessarily be 0. That means that the actual signed areas of the original spline and the translated spline are going to be identical. And another way of stating this is in terms of cyclic-oriented polygonal splines. So if we have a cyclic-oriented polygonal spline, so a1, a2 up to an, and coming back to a1 as denoted by those double arrows, so then that's automatically closed. Okay, the last point is the same as the initial point. In that case, well, the corollary is going to tell us that the signed area of what we get when we translate such a cyclic-oriented polygonal spline is going to be the same as the original area. So here's a cyclic-oriented polygonal spline, a1, a2, a3, a4, with a double arrow over it. And we're translating by vector v. So each one of these vertices gets translated by v to get this new spline up here, a1 prime, a2 prime, a3 prime, a4 prime. And we know automatically that the signed area of this thing equals the signed area of this thing. As it should be, right? That's the way it should be. But we're just checking this now algebraically. This also can be interpreted in another way. So instead of thinking about translating the spline, sometimes we can think about moving the origin, because our splines are defined in terms of the origin. Right? It's always vectors from the origin that we're taking cross products with. And now we learn that if we're talking about a closed spline, we can move the origin. Don't have to move the spline, we can move the origin. And the net effect on the signed area is 0. It's not going to change the signed area. So that's another way of interpreting the theorem also in terms of what happens when you change the position of the origin. Now primarily I'm casting the calculus, the algebraic calculus, as a theory in affine geometry. That's what it is sort of principally. And in affine geometry, the transformations which describe the symmetries of the geometry are called affine transformations. And they are of this form, where a point xy can be sent to a point like this, alpha x plus gamma y, comma, beta x plus delta y, and then plus some vector ab. So this is a combination of two separate kinds of transformations you can think of. The translation, which we've already talked about, translating by a vector, together with this more complicated transformation, which we can think of as being a linear transformation that actually fixes the origin. Okay, so this is a familiar kind of object from linear algebra, and it's usually associated with a 2x2 matrix. And so linear algebra and affine geometry have a very close connection. So it's not a surprise to us that linear algebraic ideas naturally fit into the algebraic calculus. And now I want to talk about this side of things, the effect of performing a linear transformation on the signed area. That turns out to be very important for the algebraic calculus. And we've seen special cases of it already. We have talked about this sort of indirectly, but now I want to be a little bit more formal about it and peg it down precisely. So if we just look at this kind of linear transformation here, there's some special cases that are worth thinking about. So here's a simple example of this kind of thing where we send the point xy to the point minus xy. It's easy to see that's a reflection in the y-axis. It's a reflection. So that kind of transformation is a special case of this more general thing. Another thing that we can consider is something like that sends xy to 2x 3y. This is a dilation, but it's a sort of mixed dilation because it factors or scales everything in the x direction by a factor of 2 and scales everything in the y direction a little bit more by a factor of 3. So we call it a mixed dilation. That's also included here in this general situation. And another more complicated example is the transformation that sends xy to 3/5 x minus 4/5 y, 4/5 x plus 3/5 y. This turns out to be a rotation. And it's also sort of obviously of this general form. And so this kind of linear transformation coming from linear algebra is quite useful. It incorporates at least these three different types of geometrical transformations: reflections, dilations, and rotations. So we want to understand, okay, how does such a linear transformation affect signed areas? So now here's our second theorem today, the signed area transformation theorem, which tells us what happens to signed areas when we apply a linear transformation like this. So let's call it t. Let's say that t of xy, that's a point, is this point. It's alpha x plus beta y, comma, gamma x plus delta y. And we'll suppose that we have points a1, a2 up to an, and that the images of those points are, let's say, b1, b2 up to bn. So bi is t of ai. So we're interested in relating the signed area of the spline b1, b2 up to bn to the signed area of the original spline a1, a2 up to an. And the theorem is that the new spline is a multiple of the signed area of the old one, and the multiple is alpha times delta minus beta times gamma. Alpha times delta minus beta times gamma. That's very similar to the kind of cross product expression that we've seen. It's like the cross product of the vectors alpha beta and gamma delta, if you like, the rows or the columns of the matrix that's involved here. So for example, if we're looking at the reflection that sends xy to minus xy, that'll be the case when alpha is minus 1, beta will be 0, gamma is 0, and delta is 1. So there'll only be a term minus 1 times 1 here for a grand total of minus 1. That means that this transformation multiplies signed areas by minus 1. If you have a spline and its signed area is 7 and you reflect it, then the new spline will have signed area minus 7. xy goes to 2xy, 3y. That will multiply signed areas by 6, because this is the case alpha equals 2, delta equals 3, and again beta and gamma are 0. So the product 2 times 3 is 6. That's also in keeping with our intuition. If we scale by a factor of 2 in the x direction and scale by a factor of 3 in the y direction, well, the total effect on area should be that it should scale by a factor of 6. And what about the rotation case? xy goes to 3/5 x minus 4/5 y, comma 4/5 x plus 3/5 y. Well, what's the quantity here look like? It's alpha times delta, so 3/5 squared, minus beta times gamma. Now the beta is minus 4/5. So if we take minus beta times gamma, we get altogether 4/5 squared. So this quantity is 3/5 squared plus 4/5 squared, which is a total of 1, because I've chosen these numbers from a Pythagorean triple. And so the multiple that occurs here is exactly 1. And this is in accord with the idea that this is a rotation. It leaves signed areas unchanged. All right, so to prove this, we're going to, as we did in the other theorem, look at the special case of just having 2 points to start with. So this little lemma, the same theorem really, just in the case when we have 2 points, A1, A2, we apply the transformation T to get points B1, B2, and then the claim is that the signed area of the oriented edge B1, B2 is alpha delta minus beta gamma times the signed area of A1, A2. And to prove it, we set up coordinates. There's A1 and A2. A1 is x1, y1, and A2 is x2, y2. And here are then the corresponding points B1 and B2. We apply the transformation to A1. We get alpha x1 plus beta y1, comma, gamma x1 plus delta y1. And similarly, B2 is alpha x2 plus beta y2, comma, gamma x2 plus delta y2. So now to get the signed area of B1, B2, what do we have to do? We have to take some cross products here. So we have to take this term here times this term and subtract this term times this term and divide by 2. So there's alpha x1 plus beta y1. We have to multiply that by gamma x2 plus delta y2. And we have to subtract gamma x1 plus delta y1 times alpha x2 plus beta y2. And then we divide by 2. Okay, so then we stare at this and we see that there's some cancellation. For example, the x1, x2 terms will cancel because there's an alpha gamma that appears there, and over here there's a minus gamma alpha, so they exactly cancel. Similarly, the y1, y2 terms will cancel. There's a beta delta there and a minus delta beta there, so there's no y1, y2 terms. What about, say, an x1, y2 term? We get an x1, y2 from this times this. That'll be an alpha times delta. And then also x1, y2 from here minus gamma times beta. So we get this factor times x1, y2. And what about the y1, x2 term? That's y1 times x2. So if we multiply y1, x2, there'll be a beta gamma there. And over here, a minus alpha delta. Okay. So altogether, that's the same expression, alpha delta minus beta gamma, but with a minus sign thrown in. So we can write it this way. Alpha delta minus beta gamma times x1, y2 minus y1, x2 all over 2. And that's what we wanted. There's that factor that we want. And this expression here is the signed area of A1, A2. So that's proof of the lemma, the stepping stone to the theorem. Okay, so now let's go back and prove the theorem that deals with the general splines. So with the notation of the theorem, we're interested in the spline B1, B2 up to Bn and calculating its signed area. Now, by definition, the signed area of such a spline is the sum of the signed areas of all its oriented edges. So signed area of B1, B2 plus signed area of B2, B3, all the way up to signed area of Bn minus 1, Bn. Okay, now the lemma that we've just proven tells us how to express each one of these in terms of the corresponding original spline A1 through An. So the signed area of B1, B2 is alpha delta minus beta gamma times the signed area of A1, A2. And similarly for all of the intermediate terms, all the way up to this last one, which will be expressed as, again, the same factor, alpha delta minus beta gamma times the signed area of the spline An minus 1, An. So there's a common factor of alpha delta minus beta gamma in all of these expressions, so we can take that out front. And then there is a closed expression there involving the terms signed area of A1, A2, plus all the intermediate terms, all the way up to signed area of a n minus 1, a n. But this sum here is just the signed area of a1, a2, up to an. So we get what we want. The signed area of the transformed spline b1 through bn is this multiple alpha delta minus beta gamma times the signed area of a1 through an, the original spline. This is great, and it really is an important bringing together of linear algebra and calculus. So this quantity here, of course, is the determinant of the linear transformation. That's one of the reasons why the determinant is an important object in linear algebra, exactly because it appears in this context here. It's telling us how areas are transformed, how signed areas are transformed under a linear transformation. And now we can reflect and dilate and rotate splines, and we actually have complete control over the signed area. So this theorem tells us what happens. And when we combine it with the previous theorem, we now have control over what happens to signed areas of oriented splines under general affine transformations, combining linear transformations with translations. We know how both of them affect signed areas. I want to remark, for those of you who have taken calculus before, that when you do ordinary integration and you have the x and y axes and you have some function and you're typically looking at areas under curves, that's the main object of interest in the integral calculus traditionally, areas under curves. If you take the curve, whatever it is, and you rotate it, and you ask, okay, how do we integrate this rotated curve? Well, that's somehow a little bit more problematic. That's usually not something that is so easily dealt with in this usual formulation. But we are adopting a sort of origin theoretic point of view. We're looking at areas not underneath curves so much, although we will be looking at that, but we're primarily interested in areas determined from looking at the origin. And with that point of view, this easy connection with what happens with linear transformations is really powerful for us. It allows us to easily navigate around and apply linear transformations quite pleasantly to get interesting relations between things which ordinarily maybe are not so easily connected. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.